Okay, so now we're going to be discussing about current division law. Now, similar to voltage division law, current division law applies to purely parallel circuits. First, recall the idea of parallel. The idea of parallel is we can find two common nodes that all of the elements connect to. So in this case, these two nodes are the common element are the common nodes for all the elements. Therefore, these two are considered to be, or these two resistors in this case are to be considered in parallel. Because they're in parallel, voltage is constant in this case. So the voltage drop across here is the same. However, what about the current? Well, the current, and I'm going to erase this, we have current I1 and then current I2. So the resistance, the equivalent resistance, is going to be R1, R2 divided by R1 plus R2. That's just one kind of piece of information we can extract from this. But based on KCL, the total current is equal to the sum of all currents leaving. So it's going to be, based on KCL, the sum of all currents entering or leaving a node should be equal to 0. We have a node here. We have a current I and two nodes leaving and two currents leaving. So we have something like this. Now, for current I1, we see that it's the same voltage source. So it should be just V divided by R1. Similarly, we have V divided by R2. We can factor out V, and we get 1 over R1 plus 1 over R2, which leads to I divided by V equal to 1 over R equals to 1 over R1 plus 1 over R2. And that's just the relationship that we just saw with the equivalent resistances. Now, with this in mind, though, if we were to ask what is the current across R1, we can see from this equation that it's just going to be V is equal to, well, it's going to be equal to I divided by 1 over R1 plus 1 over R2. So it's going to be V divided by R1, or equivalently, I divided by, it's going to be equal to V over R1. Now, of course, it equals to this really, really ugly reciprocating formula. However, if we do common denominator and start simplifying, this becomes I divided by R1 plus R2 divided by R1, R2 divided by R1. These two R1s cancel out. And this R2 goes at the bottom. So at the end, or it goes at the bottom, which flips it to the top. So I1, therefore, is going to be R2 divided by R1 plus R2 I. Notice that instead of getting the same resistance, we're getting, or instead of asking about knowing about the resistance here, we need to know about the resistance here. So anytime you want to find the current of one part, it's equal to the resistance of the it's equal to this, which states that we must know the resistance of the other resistor divided by the sum of the resistances. Now, to keep it more general, suppose you were asked to find just the nth current of some loop, or of some the nth current of some purely parallel circuit. To do this, this is just equal to 1 over Rn divided by the sum of 1 over Rk times I. The reason why we have to keep it this way is simply because in general, it should be Rn. The reason why we have to keep it this way is because sometimes you might have 3 resistors, 4 resistors, 5 resistors, and this already kind of makes then the formula a little more complicated. So what ends up happening is, based on this observation right here, we don't have to simplify this. We can just move this to the bottom and move this to the top. And so we just have the reflected resistance of I1, which is R1, divided by the sum of the reciprocals of the resistances, which is what we have over here. Now, experimentally, experimentally, you may want to avoid a current divider. Avoid current divider. Why? Let's say you had a variable resistor, and then you had a really tiny resistance, like so. Let's say this was 100 ohms and this was 500 kilo ohms. I asked what is the current on this one. Well, I1 is just going to be equal to the opposite resistance divided by 100 plus 500k. If we crank it up all the way, that is. Now, what if this is not this is not the value, but rather it's a suggestion of the maximum range. So it could go from maybe 0 to 500,000. Now, what if I cranked it to 0? Well, then I will get, if I crank this to 0, this will go away. Then we have just I1 equal to I. And this will basically flood will flood current through this junction and basically may damage your circuits. So we would always want to avoid a current divider experimentally, but theoretically, this is how we construct a current divider. In general, current dividers are not bad. They are useful for biasing, for bias currents, for operational amplifiers. However, experimentally, we can't use it to control too much stuff. And in general, if we want to control something, we generally want to avoid a current divider. We always want to use a voltage divider. So that's just some information. Okay, thank you.